Hello, today we're going to review how to distinguish between the different types of chemical reactions. So let's do a quick review of the 5 basic types. We have combination, which is where you have 2 separate things combining into one molecule or compound. We have decomposition, which is when you have a compound or molecule splitting apart into different components there. We have single replacement or single displacement, depending on how you want to call it. It's where a single element is reacting with a compound, and then it will switch partners like this. Double replacement is when you have 2 compounds reacting and they switch partners. And then, of course, combustion. And combustion will be a reaction with oxygen gas. If you have a metal reacting with oxygen gas, it will combine. And then if you have a hydrocarbon reacting with oxygen, it will form CO2 and H2O. Now remember, these specific subscripts will depend on the specific elements involved or the specific molecules involved. But those are like the general types of reactions there. Double replacement is not a redox reaction, but the other ones are. Single replacement, I want to get a little bit more specific here with single replacement. It's the only one that you should really check what we call an activity series. The element that is by itself needs to be more reactive than the same type of element in the compound. So for example, if A is a metal, it needs to be a more reactive metal than B. And as long as it is a more reactive metal, then that reaction will occur as written. But if A is not more reactive, then this reaction will not happen and you would put no reaction. So the element by itself must be more reactive. Now another example of that would be if you have a nonmetal, so let's say all these different letters. If E is a nonmetal, then you would form something like this, where the nonmetal is going to swap with the nonmetal in the compound. But again, and I'll label this single replacement as well, because it's also single replacement. So the element by itself, the nonmetal in this case, must be more reactive than the nonmetal in the compound in order for this reaction to happen. And if it's not more reactive than the element in the compound, you would just say no reaction. So you can distinguish an acid-base reaction because there's a transfer of a hydrogen ion. So a really common one would be hydrochloric acid and sodium hydroxide. Whoops. So what happens here is it's still a type of double replacement. We have 2 compounds, so they're going to swap partners. The sodium will wind up with the chlorine, and the H will bind with the OH to form water. But if you can see that there's a hydrogen ion being moved from one partner to a different partner, anytime the hydrogen ion is moving, that is an acid-base reaction. We also call hydrogen ions just protons a lot, so you'll see it called a proton transfer, and that's because hydrogen ions are just a single proton. Typically, occasionally they'll have 1 or 2 neutrons, but they don't have any electrons at all, so a lot of times we'll just call them protons. So an acid-base reaction involves the transfer of a proton. Now, oxidation reduction reactions. A lot of time we will abbreviate this as redox for oxidation and reduction. I assume because it sounds better than oxred. But there's an acronym that we can use, and there's a couple different ones, but I like oil rig, where it stands for oxidation is losing electrons. And then reduction is gaining electrons. So the substance that is oxidized loses an electron over the course of the reaction, and the substance that is reduced gains an electron over the course of the reaction. I've also seen Leo the lion says grr, so Leo and grr, where losing electrons oxidation, gaining electrons reduction. Either way you want to remember it, you do need to make sure that you remember it. And as long as there is some kind of transfer or change in the number of electrons in any given substance, that is a redox reaction. If there's no change in the electrons, then it is not a redox reaction. Typically, double replacement reactions are not redox reactions, but the other four types are redox reactions. The best way that we have to figure out if an atom is gaining or losing electrons is by using what we call oxidation numbers. Now, oxidation numbers are always written with the sign first and then the number. Sign first, then the number. That's to distinguish it from charge. And for the charge, we put the number first and then the sign. But oxidation numbers just kind of tell us the potential to gain or lose electrons. And there's a few rules for figuring them out. So if you have an element in its elemental form, so basically by itself in its standard state, an elemental form, then its oxidation number will be 0. So like O2 or H2 or just solid sodium, any element by themselves in their standard form. Oxygen and hydrogen are diatomic, so their standard form is with a partner. So the way that we remember those diatomic ones is Brinkelhoff. Okay, so those are the diatomic elements that you need to remember. Bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine makes Brinkelhoff. All of those exist in pairs, and all of those, if you see them, will have an oxidation number of 0. Monatomic ions. Remember, mono means one, atomic, single atom there. Monatomic ion, single atom ions will be the same as the charge. The oxidation number will be the same as the charge on that ion. Oxygen will have an oxidation state of -2, except in peroxides, so like except hydrogen peroxide. It's basically the only peroxide that we see. And then hydrogen in a compound will have an oxidation number of +1, except when it's a hydride, in which case it will be -1. That's where if you have a metal like sodium binding to the hydrogen, it doesn't show up very often at all. And then last but not least, the other elements. Any other elements, you're going to have to make sure that they add up to the charge on the compound or ion. And I'll give you a couple examples of that. Let's try out ClO3 negative. That's the chlorate ion. So chlorate, we've got oxygen in a compound, and it's not a peroxide, so the oxygen is going to be -2 for sure. But we don't know the chlorine. Okay, it's not a monatomic ion. It's not in its elemental form. So I don't know what the chlorine is. So we have to make sure that these elements add up to -1 because the charge on the compound is -1. So something from chlorine plus the -6 from those 3 oxygens need to add up to -1 for my overall compound. So the chlorine must be +5 in that situation. Another one would be if I have just SO2, oxygen is -2 in a compound, and since there are 2 of them, it's -4. there's no charge on this molecule, so your oxidation numbers need to add up to 0. So something plus -4 will give you 0, so the sulfur must be +4. Now this is important because if you see any elements on the reactant side changing to a new oxidation number on the product side, that means that there was a redox reaction that happened. So if we have an increase in the oxidation number, the element was oxidized. Remember oil rig, so if you increase the oxidation number from the reactants to the products, it must have lost electrons, got more positive, and therefore was oxidation. Now if you decrease the oxidation number from the reactants to the product side, the substance was reduced, and that's where they got that name reduced from. So if you're decreasing the oxidation number, remember reduction is gaining. It's getting more negative because it's gaining electrons, and electrons have a negative charge. So again, this is from the reactant side to the product side, if that's changing. If none of the oxidation numbers change for the whole reaction, then it is not a redox reaction. The last main type that you need to be able to recognize is precipitation reactions, which we talked about a lot with net ionic equations. So really, precipitation reaction is anything that will form a solid product. So something like CaCl2 and sodium carbonate will do a double replacement reaction here to form calcium carbonate, which is a solid precipitate, and sodium chloride, which is aqueous. Now, you should always write this as a net ionic equation, so you will eliminate any spectator ions. Anything that's aqueous splits up into ions, and anything that's solid stays the same. So we wind up with 2 calcium ions and 1 calcium 2+ ion and 1 carbonate 2- ion will react to form calcium carbonate as a solid. I eliminated the sodium and the chloride ions because those are our spectator ions. And again, anytime you see that solid being formed, it's a precipitation reaction. And make sure you go back and review the net ionic equations video if you need a review on that stuff.